Hello, buddy. Welcome. So, today we're really going to talk about matrix groups. Matrix groups. Or matrix group, depending on how you want to call it. Well, so, before we get a little general, we're going to start a little simpler, right? So, consider this set G. Let G be the set of all 2 by 2 matrices, right, under multiplication, where the entries A, B, C, D are of the form all complex numbers, right? So we say that this is the set of all 2 by 2 matrices where the entries are complex numbers. So we actually have a special name for this. We refer to it as GL2C. That is the general linear group, or rather as the set of two. It's the same as saying the set of all 2 by 2 matrices with complex entries, right? We usually refer to it as GL2C, right? If you take further classes in abstract algebra, it will make perfect sense why this name is given. But most important of all, we need to find out. We are claiming that this thing here is actually a group, right? And it's such an important group that I'm dedicating a special video just to it to explain how it works. But first, let's prove that it's a group, and let's see why it's so special, right? Let's start with proving that it's a group. To prove that something is a group, remember, we need to prove 3 properties. One, we need to prove that it's closed, right? If you're a group, then you're closed, right? The second property of a group is that it has an identity. There exists. Wow, my pen is not so good. There exists an identity element. The other thing we need to prove is that every element has an inverse, and the inverse is an element of the group itself, right? And the other thing we need to prove is associativity, right? We need to prove associativity, right? So let's proceed step by step here to prove these things. Well, so consider any 2 by 2 matrix, right? So we have our first 2 by 2 matrix A, B, C, D, and we have our other 2 by 2 matrix E, F, G, H. To say that GL2C is closed means the product of any 2 matrices in GL2C, or in G in this case, must also give us 2 by 2 matrix with complex entries as well, right? Well, notice when we multiply matrices, it's row by column. So when we multiply A by E and B by G, the answer we get is some complex number. Similarly, row by column here, we have some other complex there. Then we have a complex there, and we have a complex there. So the end result is indeed a 2 by 2 matrix with complex entries, right? So this tells us that any 2 elements of this set here, GL2C, is such that the product of any 2 matrices give you something that's within the group. That is to say, GL2C is closed, right? So the other thing we know for sure is that there exists an identity. The identity is exactly what you're going to guess it is, and what you've probably seen before in a linear algebra course, perhaps. We're going to call this thing here our identity. Notice, when I do the multiplication, I actually have A here, row by column, this is B, row by column, this is C, row by column, that is D. So it then appears that this thing here, which we're calling I, the identity, right, the identity matrix, does absolutely nothing to ABCD. ABCD hits it, and you get ABCD back. Nothing happens, right? So this tells us that we have an identity element. That's done. The other thing we need to see about GL2C is the property of inverses. And you've probably seen this before as well, but if I have ABCD, right, a matrix in GL2C, and I want to figure out its inverse. Well, its inverse is actually given by 1 over AD minus BC times, let me see if I remember correctly, DA minus C minus B, right? So again, there is actually a process that shows how this comes about, but I write it here, and if you want to verify that it's true, you can do that. And if you want to see the derivation, well, you could probably look online for it, right? But the point is that every such 2 by 2 matrix actually has an inverse, right? And the thing to note here is that this 1 over AD minus BC multiplies into here, 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 and here. And so the end result is that you have a 2 by 2 matrix once again with only complex coefficients, complex entries within it. And that tells us that this inverse right here for this matrix, the inverse of this matrix is also an element of GL2C, right? And so that completes our proof that elements of GL2C are actually invertible. They have inverses. Well, associativity from multiplying matrices, I'm sure you've seen this before, is that if I have two matrices A, B, C, right? Well, let me erase that. I'm getting too excited. If I have two matrices A, B, C, right? So I could multiply A and B first, and then multiply the answer by C, but that is really the same thing as if I did B times C, right? So this is something that can be verified by actually doing the multiplication. I'm just not going to do it here, right? And so then we see that GL2C actually satisfies associativity. Well, if GL2C is closed, has an identity, every element has an inverse, and it's associative, then we say that GL2C is a group, right? So why are we so why is this such a big deal? Why are we so happy about GL2C? Well, the reason why we are happy about it is because GL2C is an example of a group that is actually what is called non-abelian or not commutative. That is, for all the groups that we've been looking at, right? For example, we've been looking at Z under addition, right? The integers under addition. We notice that we know that 2 plus 3 is the same as 3 plus 5. 3 plus 2, sorry. It doesn't matter whether you do 2 plus 3 or 3 plus 2. The order doesn't matter, right? We looked at other examples, of course. We saw something like Q without 0, right, under the property of multiplication. And we knew that, for example, 2/3 times, let's say, 4/5 is really the same as 4/5 times 2/3. When you look at these examples, it might be easy to conclude and somehow think to oneself that really the order doesn't matter, right? But it actually does, and GL2C is perfect because it shows us this. Consider these two matrices, right? So let's call matrix A, we're going to call matrix A 1 1 0 0. It's a 2 by 2 matrix, a member of GL2C, and the entries are definitely complex. Let's get another matrix within the same group, 0 0 1. Right, now let's compute. What's AB? Well, AB would take us row by column, so that would be 1. Row by column 1, this would be 0 0. And BA, right, row by column, right, this is going to give us 0 0 1 1. Actually do the multiplication to check that I'm correct here, right? And what do you notice? AB does not equal to BA. So we have a group in which the order in which you multiply things matters, right? And so this is what we say when we do this. We're saying that GL2C is an example of a non-commutative group, right? When the order doesn't matter, as in the case of GL of Z, the integers under addition and the rationals under multiplication. When the order doesn't matter, we say the group commutes. But when the order matters, we say it's non-commutative, as in the case of GL2C, right? And obviously, GL2C can actually be generalized, right? It doesn't have to be 2 by 2 matrices. You could have 3 by 3 matrices, in which case you're looking at GL3C. You could have 4 by 4 matrices, right, with complex entries, in which case you're looking at GL4C, right? In fact, in general, by similar methods, you can prove that GLN for any n natural number is also a group and is actually in general non-commutative as well, right? And so this is really useful because there are many problems. Sometimes you have a problem you're trying to solve, and the problem is talking to you about a non-commutative group. And so a perfect example to use is GLNC, because GLNC gives you some interesting insights into non-commutative groups, and it's also usually a perfect source of counterexamples, as you'll see in an upcoming problem set, right? Or an upcoming problem. You'll see why. You'll see how GLNC can actually really simplify life. Well, there are also some small subsets of a matrix group. For example, there's something we call, let's start basic here. We call it, let's say, SL2C. That is the special linear group, which is really the set of all 2 by 2 matrices, let's say A, B, C, D, such that, of course, we want A, B, C, D to be complex numbers, but in particular I want to insist that each of these matrices must satisfy the property that its determinant must equal to 1, right? It actually turns out that SL2C is also a group, right? And I leave that as an exercise to you to verify that it's a group. But as a hint, oh, maybe, what the heck, let's actually prove that it's a group. How are we going to prove that it's a group? Well, one is that it must be closed, right? Second thing is it must have an identity element. It must be invertible, right? That's a third property. And the fourth property is that it must be associative, right? Well, these are still 2 by 2 matrices, and so we already proved associativity as in the case of GL2C, so that's not a problem, right? Identity also is not a problem. We just use the same identity as before, right? The identity, this identity here, because as we notice, its determinant is actually equal to 1, right? Determinant would be this times this minus this times this. That's 1 minus 0, which equals to 1. So the identity is an element of SL2C, and in particular it also works, so it's really the identity for the group as well, right? So that comes easily to us. Well, invertibility, let's look at invertibility, right? Or maybe closure first. Well, if you have a matrix A that's an element of SL2C, right? So A and B are 2 matrices, and both of them belong to the special linear group on 2 by 2 matrices, SL2C. Well, to prove closure would mean we want to prove that A times B is also an element of SL2C, right? That's what closure would mean. Well, notice, to prove that something is an element of SL2C, we know that A times B, we already proved it before, that A times B is the set of each of these is elements, they're elements of SL2C, but they're also elements of GL2C, right? Because GL2C is also the set, I think we saw it here, is also the set of 2 by 2 matrices with entries that are complex. It's just that we don't always specify the determinant has to be 1, right? And so that really tells us that any element of SL2C is actually an element of GL2C, right? And so when we multiply A times B, we are going to get still, because GL2C is closed, we are going to end up with the outcome, the new matrix we get when we multiply A times B is definitely going to be a 2 by 2 matrix with complex entries. Our main question would be now to figure out whether it's an SL2C, would be to figure out whether the determinant, right? Alright, we've reached the point again where the pen decides not to cooperate. So would be our main task would be to prove the determinant of A times B, right, also equals to 1. That would be the task. But it's actually known in linear algebra. Again, you can look this up or try to derive it, right, depending on if you're so inclined. But it really is true that the determinant of A times B equals to the determinant of A, right? This is a known fact that's really useful. is equal to the determinant of A times the determinant of B. Right? Determinant of B. Well, but we know that A is an element of SL2C, so that means the determinant of A then must equal to 1. We also know that B is an element of SL2C. That means the determinant of B must also equal to 1. And so the determinant of A times B, which is 1 times 1, also equals to 1. That tells us that A times B is also a member of SL2C. Right? And so what that really implies to us is that SL2C is closed. Right? As pertains to invertibility, well, get any A. Let's take any A element of SL2C. Right? 2 by 2 complex numbers. Right? Well, we know that an A inverse exists, right? Because again, elements of A are also elements of GL2C, right? They are still 2 by 2 matrices and they still have complex entries. The only thing is, for A inverse, we know it's a 2 by 2 matrix with complex entries. What we don't know is whether its determinant actually equals to 1. That's what will help us to know whether the inverse is an element of SL2C. Right? Well, again, this is from linear algebra, but the determinant of A inverse is actually given by 1 over determinant of A. Right? And once you know this neat fact, we know that A is an element of SL2C. So that means the determinant of A equals to 1. And so we now see the determinant of A inverse equals to 1 over 1, otherwise known as 1. So that means that A inverse is also an element of SL2C. Right? And so that means that every element of SL2C is invertible. Well, if SL2C is closed and has an identity and is invertible and is associative, well, that means that SL2C is actually a group, right? And that in particular means that actually this SL2C can be generalized just like GLN was generalized. You could talk of SL3C, right? The set of all 3 by 3 matrices with complex entries such that the determinant is always equal to 1, right? And you can actually generalize this to SLNC, right? It's exactly what you'd expect it to be. The set of all n by n matrices with complex entries such that the determinant of each of those matrices equals to 1, right? And so these are two groups that are really important, right? And as you might be guessing, it really is true that SLNC is actually a subgroup of GLNC. I'll leave it as an exercise for you to prove that this is true, right? So thanks very much for watching this video, and I hope to see you on the next one.